Okay, let's start. So today we are starting, I think it's chapter 6, but yeah, it is chapter 6. But we're starting the chapter on probabilities. So next chapter we're going to be calculating probabilities. I'm sure that you've calculated probabilities in the past tons of times. If I were to ask you what's the probability of flipping heads twice in a row, what is it?
25%.
25% or 1/4, however you want to think about it. Now, you're going to notice as we start chapter 6, we're going to start by building a mathematical model called a sample space. And we're going to use this sample space to calculate probabilities. And at first, since the probabilities, you've already had some education in this, are very intuitive for you, it's very easy for you to calculate basic probabilities, it's going to feel very tedious to you to have to use a sample space to calculate a probability when you already know how to do it. So the point here is not to teach you that the probability of flipping heads twice in a row is 25%. So when you are doing your homework problems and you're calculating a probability, I don't care that you figured out 25%. That's not what I'm after. The point of this section is to teach you how to use a mathematical model called a sample space to calculate probabilities and to determine probabilities. And it's going to feel tedious at first, but as you get further into probability, the complexity in calculating probabilities shoots up. It's a topic that early on feels very intuitive, feels very easy, but even really, really basic questions can kind of throw you off. Did we already talk about the Jack and Jill problem? Jack and Jill have 2 kids. One of their kids is a boy. What's the odds that their other child is also a boy?
50%.
50%. This is a trick question. 50%, right? No! See how easy it is to throw you off? Jack and Jill have 2 kids, right? So, we got that. And I tell you, one of them is a boy. So what are all the possibilities? They could have had a boy then a girl. They could have had a girl then a boy. Or they could have had 2 boys. All those are equally likely. What's the odds that their other child is also a boy?
30%.
Right, so we would call S, this is our sample space, this is how we're modeling the problem, and we're saying that the probability of each of these, the probability of boy and girl is equal to 1/3, the probability of a girl and a boy is equal to 1/3, and the probability of a boy and a boy is equal to 1/3. So there we were, very, very basic probability question. You already had intuition about how everything worked. The sample space was very teeny, just 3 members, and it's real easy for you to lose track of, get the problem wrong, your intuition to mislead you. So this is very dangerous when you get to probabilities. Early on, things seem very intuitive. You think you just got it, and so you don't want to bother setting up the sample space. The point is, set the sample space.
Is that
That's
what
what
the
we're
sample
teaching.
space looks like?
So yeah, the sample space is the ordered pair S comma P. Not identical, very similar to how we define a topological space. Topological space, you have a set of things, and then you give those set of things some structure. That's exactly what we did. We took a set of things, and now this is giving them some structure. So P, if we write it more explicitly, P is equal to the set of ordered pairs, BG goes to 1/3. GB goes to 1/3. And then BB goes to 1/3. So this is a sample space where S is this set and P is this set. That's an example of a sample
And that's
space.
how we'll be writing it out in our homework?
Something like that.
Okay.
Well, this was just meant to be a high-level conversation, not to get to the nitty-gritty yet. Let's get to the nitty-gritty, then we can move on to how exactly we write this out. So what exactly is a sample space? A sample space is an ordered pair, S comma P, where S is a finite, non-empty set, so just some finite collection of anything, and P is a function from S to R. You remember what this notation means? P is a function that maps everything in S to some real number.
Okay.
Over here, we map this to 1/3, this to 1/3, this to 1/3. P is a function that maps everything in S to some real number, to something in R. So, a sample space is this ordered pair, S is a finite non-empty set, and P is a function like this, such that we require P to meet two conditions. Condition 1, the probability, this function we call the probability function, so I'm going to accidentally say that, but I'll try to avoid it. So, such that, I have to say it, the probability of any particular event in our samples in S is always greater than or equal to 0. P always maps to real numbers greater than or equal to 0. That's one way to say it. All these right-hand elements have to be greater than or equal to 0. That's the first condition. And the second condition is that the sum of all our right-hand values in P have to equal 1. Intuitively, what are we saying? We're saying negative probabilities don't make sense, and there's always 100% probability that you get one of your outcomes. That's the intuition. So for the example we set up over here, there's a 100% chance that if you know one of them are a boy, there's a 100% chance that it's one of these, and a 33% chance that it's this one, or it's this one, or it's this one. There's no such thing as, well, there's a negative 24% chance that they had a girl and a boy. That doesn't make sense. So negative probabilities don't make sense. So this probability function satisfies two criterions. The first one is that each number that it pairs an S with has to be greater than or equal to 0. 0 is perfectly fine. Up here I could have also done this. I could have done or girl, girl. But we know that probability of girl, girl is equal to 0. Right? And we're still fine. Anyways. So that's what a sample space is. Sample space is a pair SP where S is a finite non-empty set and P, the probability function, is a function from S to R such that for any little s and big S, its probability is greater than or equal to 0, and such that the sum for all little s's and big S of their probability adds up to 1. Good? Any questions so far? Alright, so now let's move on to examples and maybe one more comment now that we have a sample space. So a sample space, one of the cool things about first getting into this section is it gives you a nice little taste of where science begins. So one of the most fundamental jobs of science is to come up with a mathematical model that accurately captures some physical phenomena. So you start with some physical phenomena in our universe, and then you try to come up with a mathematical model that captures that physical phenomena, and that's useful for making predictions down the road. If its predictions are accurate, we say it's a good model. If its predictions aren't accurate, we say it's a bad model. That's ultimately what science does. So we're going to do a bunch of examples where we create a sample space. So the reason I'm stressing that is there's no such thing as, when you come across some physical event, there's no such thing as the right sample space versus the wrong sample space. There's just useful versus not useful. That's it.
Okay.
So there isn't the right one. There's choices in how you decide to set your model. So we'll look at an example. Consider rolling a die. We've got a 6-sided die. I'm rolling the 6-sided die. And we're going to create a sample space, SP, for that. Now here's one sample space that we can make. I can say my sample space is going to be 1, 2, 3, 4, 5, 6. And obviously that's corresponding to the number of dots on a particular side of the die.
Yeah.
And I could have said, and the probability of rolling a 1, I want to be 1/6. And of a 2, I want to be 1/6. A 3, I want to be 1/6. 4, I want to be 1/6. 5, I want to be 1/6. 6, I want to be 1/6. Perfectly valid way to do it.
Yeah.
Right? I could have also set it up this way. S is this set. Anything wrong with that set?
No.
No. It's just a non-empty finite set, and I'm using this to capture rolling a die. It's just as valid. You can't tell me this one's right, this one's wrong, or this one's right, this one's wrong. It's just a matter of what's useful. If it's useful, it's useful. And the probability function, notice how I did the probability function here. I said the probability of ruling 1/2 of 1 is 1/2, of 2 is a tenth, 3 is a tenth, 4 is a tenth, 5 is a tenth, 6 is a tenth. Now notice up here, all these probabilities added up to 1. But down here, what do all these probabilities add up to? 1. So it's still a sample space. This is a sample space, this is a sample space.
Even though the second one really isn't that true?
What do you mean isn't that true? You don't know if it is true or not true. There are two different sample spaces for a physical phenomenon. Now you might say, that one appeals to my intuition as being more useful, and that one maybe not. Maybe when I created this sample space, I was working with a loaded die. There's only one way to determine which one's more useful, and that's to go out and play with the die, right?
Okay.
Right? Because if it is a loaded die, and it's loaded towards 1, mine's going to be way more useful than yours.
So you're saying it really doesn't matter whether it actually appeals to our intuition or not. It's whether it meets those requirements in the definition.
A sample space just meets these requirements. And a
Okay.
sample space is a sample space. And whether it's useful or not is whether it's useful or not. Those are two separate questions. This is a valid sample space versus this is a useful sample space.
Okay.
If we're talking about a fair die, this is a useful sample space, this one isn't. If we're talking about a loaded die on a 1, then this is a more useful space than this is. But they're both perfectly valid sample spaces for the phenomena we're talking about, right? Because they meet the two requirements. Well, 3 requirements. You have a set and a function defined on that set. The functions, all its values are positive, and all its values add up to 1. Same thing down here. So it's a sample space. Right?
Yep.
Pretty straightforward. So let's do one. So we're out strumming around the universe and we come across a little spinner like this. Yeah? Just out there floating in space. We're like, that's interesting. Let's make a sample space for it. So how does this thing work? There's a little arrow there. You flip the arrow, it spins around and it lands on something. We want to create a sample space that's useful for this spinner. So what might our S be that we use in our sample space?
1, 2, 3, and 4.
Yeah, we could have S's 1, 2, 3, 4. What's another way that we could have had S?
Blue, red, orange, green.
Blue, red, orange, green. So we could have had a blue, red, orange, green. Which of those is right? The one with numbers, because we're in a math class.
Obviously.
Unless you want the math to look smart, then you put letters in there. Confuse people. Right?
Algebra 101.
Alright. So yeah, both those are perfectly valid sample spaces. Now, what's a probability function that we might use?
1.
Using this as our sample space.
Okay, 1 pairs with 1/2.
Yeah, that looks like it's about 1/2, right?
2 pairs with 1/4.
Yeah, that looks like it's about 1/4.
3 pairs with 1/8. And 4 also pairs with 1/8.
And 4 also pairs with 1/8. Right? Now obviously, if we were to be more fine-tuned in our measurements, we would find out 3 and 1/8. Are you kidding me? This one is closer to 7/64. And this one's closer to 9/64. Could you be more wrong? Right? And we can make finer and finer measurements of this thing and get a more fine-tuned sample space, but that's just making it more useful. The sample space we had was still a sample space.
Okay.
And he was guessing that based off of our picture and how rough everything was, that what we had was good enough. It was close enough. So yeah, that's perfectly valid sample space. Perfectly valid probability function. Let's look at this one. Let's say B, that's a 0, no chance. R, that comes out at about, I don't know, 1/3. O, minus 1/3. And G, yeah, we're going to get a G. Is that a probability function?
No.
No, what's wrong with it?
There's a negative.
There's a negative. Is that the only problem with it? It goes over 1? No, it doesn't.
No, it
A third
doesn't.
plus
Yeah.
1 minus a third is 1.
If you fix the negative, there might be a problem with it.
There's a potential wrong if we made this a third and this a third. Are we okay now?
Yep.
Yeah.
We are?
Yep.
That's a 0, not an O.
Yes.
You praising my ability to identify numbers? Yep, you're right. Yeah, that's perfectly fine. So, 2 different sample spaces for the exact same physical phenomenon. We would guess one of those is much more useful than the other. Okay, let's do it again. So now we're talking about the example of rolling a pair of dice. So I have assumed 6-sided die. I have 2 6-sided die. I rolled the 2 6-sided die. What might our sample space look like for that? So our set of possible outcomes, that's what we mean by S. S is a set of possible outcomes. That's how we typically refer to it, and this we call the probability function. So what would my set of possible outcomes look like?
2 to 12.
2 to 12?
Yeah.
Okay, so he's thinking about it the hard way. So Peter's thinking we can have 2, 3, ... all the way to 12. Is there another way we could have it?
Couldn't this just be either of the dice? So the first dice and the second dice? And you get a number from one of them? Does that kind of make sense?
You guys are overthinking a little. 1, 2, 3, 4, 5, 6, crossed with 1, 2, 3, 4, 5, 6. So that if I roll a 3 and a 1, that's represented with 3, 1. Right?
No. I think you got what I said on that, but not on the probability.
Oh, that wasn't a probability. I was saying that's what it was.
Yeah.
Because now, look at if you use mine. For mine, what does my probability function look like?
It's ordered pair, and the first element is going to be ordered pair.
But in general, it's just P of S is equal to 1 over 36. Doesn't matter what outcome you pick, there's a 1 in 36 chance I roll it.
Mm-hmm.
What's the odds that I roll a 2 and a 3? 1 in 36. If you do it this way, what's the probability of a 2?
136.
1/36. What's the probability of a 3? 1/18 or 2/36. What's the probability of a 3?
Didn't you?
It just counts up.
36.
3/36. What's the probability of a 4?
446.
36.
There's 5 of them. No, there's only 4. Yeah, it just counts up.
Why is it counting up?
I feel like you asked us the 3 1 twice.
1, there's only one way to get a 1. 2, how many ways, or 2, there's only one way to get a 2. How many ways are there to get a 3?
2.
2 and a 1, 1 and a 2.
And you said there was 336 on 3.
Oh, I
At
did?
least I think you did.
Oh, did I say the same one twice?
Yeah, I think you did.
Okay, that makes sense. Why is that the case? If you look at the table, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now we've got to make a grid for all our rules. The reason is these are your 1s, these are your 2s, or sorry, these are your 2s, these are your 3s, these are your 4s, these are your 5s. You see what I'm saying? 1, 1 is the only way to get a 2.
Mm-hmm.
2, 1 gives you a 3, and 1, 2 gives you a 3. 3, 1 gives you a 4. 2, 2 gives you a 4. 3, 1 gives you a 4. 4, 1 gives you a 5. 4, 2, or 3, 2 gives you a 5. 2, 3 gives you a 5. 1, 4 gives you a 5, etc. So,
Okay.
so it's going to come all the way until we get to 7, and 7 there's a 1/6 chance of rolling 7, and then it counts back down. So 6, 36, and 4, 8, 5, 36, 4, 36, 3, 2, 1, 36, once you get back to 12. Right? So with this sample space, then your probability function gets messier, but it works. But if we use this sample space, then our probability function is just P of S is equal to 1 over 36 for all S in S. Right?
Okay.
And this is the natural one to use. Okay, let's do another example. Let's set up a sample space for a poker hand. You all understand what poker is and basically how it works? You're dealt 5 cards based off of how good your cards are, you win or lose. But you just have a hand of 5 cards.
Depends on the poker, but yeah.
And, well, even if it's Texas Hold'em, you're using a total of 5 cards.
Yeah.
So consider a poker hand. It's just 5 cards out of a regular 52 card deck. Right?
Mm-hmm.
What would S be? You can just say it in words. I don't expect you to, huh?
What?
What would S be?
S would just be 5 different cards, right?
It's the set of all possible sets of 5 cards. It's the set of all possible poker hands you can get.
So is it
Okay.
52, is it 1 through 52 cross 1 through 52, and you do that 5 times? Is that what you're saying?
Let's see. No, not that, because you can't repeat cards.
Oh, I see.
That's true.
So it's the set of all 5 element subsets of the set of 52 cards.
Wait.
So what might it look like?
To go along with what you were saying, wouldn't it be 152, 1 over 50, whatever, 1 to 52, cross with 1 to 51, cross with 1 to 50?
I'm pretty sure that's assuming that, like, the card that you got the first time would have been 52 or something like that. Like, you could still have repeats.
No, what you saying makes sense.
Yeah, because then you're taking out that repeat card.
Yeah. So it's 52.
Oh, I guess if the
Because it doesn't matter what card you're taking out, right?
card represented by the number changes with each set that you're crossing.
Then
It's the set of all possible hands of cards. So I'm saying here's a possible hand. You have the ace of hearts, the 1 of hearts, not the 1 of hearts, 2 of hearts, 3 of hearts, 4 of hearts, and 5 of hearts. Okay. There's a possible poker hand, right?
Okay.
So that's one possible hand. S is going to be the set of all possible hands. Question, what's the size of S? How big is S? How many possible poker hands are there? How many cards are in a deck?
52.
52. How many 5 element subsets can I make from a 52 element set?
Just 52 times 5, right?
Not even
No.
close.
No.
No, it's 52 times 51 times 50 times 49 times
So it's
48.
52.
No, it just stops at 48, I think.
How many ways can I choose 5 cards from a 52 element set?
52, choose 5.
Oh, there it is. 52 choose 5. Which is the same thing as 52 factorial all over. Where Emma was going, she didn't quite finish it yet. 47 factorial, also divided by 5 factorial. You have to divide by 5 factorial because order doesn't matter.
Oh, right.
You remember that choose notation?
Yeah.
Yeah. How many ways can you choose 5 cards from a 52 element set? Don't know a bigger giveaway than that. Okay, so that's the size of S, right? Now, what is our probability function gonna look like then? What's the probability of getting a particular little s and big S? You know what I mean by probability of a particular S?
And
I'm saying one of these things. What's the probability of getting this thing right here?
1 over 52 choose 5.
1 over the size of S, or 1 over 52, choose 5. They're all equally likely. Each hand's equally likely, right?
Okay.
So, there's the answer. That seems like a pretty useful sample space for a poker hand, right?
Yeah.
Okay. Now, tossing a coin. Here's another one that you've come across before. Intuition question. Let's see if you get it. Is it more likely that I flip 2 heads, or that one of my flips is a heads and one of my flips is a tails? If I have 2 tries to flip a coin, what's more likely? That they're both heads, or that one of them is a heads and one of them is a tails?
It's the same.
It's the same.
It's the same, right? Because in one case you get heads, heads. And in the other case you either have heads, tails, or tails, heads.
No, they're
So
not.
no,
They're not the same.
it's twice as likely. There's 2 ways to do this, only one way to do this. Here's all your possible flips if you're flipping a coin twice. 2 of them give you 1 heads and 1 tails. Only 1 of them gives you 2 heads. You lose again.
So wait. So that's 1/4, right? So 25%.
There's a 25% chance of flipping heads, heads, 25% chance of flipping heads, tails, 25% chance of flipping tails, heads, 25% chance of flipping tails, tails.
Yeah. What was your question again?
My question
It's the
is,
same coin.
is it more likely that you'll flip a heads twice, or that one of your heads, or one of your flips will be a heads and one of your flips will be a tails?
If it's the same coin, then it's.
So I guess that's 50 to 25%, right?
Yeah.
Okay.
It is twice as likely that this happens. You're like 100% off. It's the same amount.
It's still.
It's still 50-50?
Yeah.
Okay, we'll play a gambling game. We'll get a coin. You flip it twice. If both of them come up heads, I give you $1. If one of them comes up tails, you give me $1. Unless both of them come tails, then nobody wins. So if this happens, I win. If this happens, I win. If this happens, you win. Let's play for a little bit. As soon as I have enough money, you'll believe me that it's true. Why is this less likely than this?
It's not less likely.
Why is this less likely than this?
It's not.
So this is the same likely as this, and this is the same likely as this.
Okay, I see what you're saying, but if it's the same coin.
No, we switched coins. We used
No.
one coin for this one, and then we went and found another coin for our second flip.
That makes sense.
Well, that's only up here. Down here, we use the same coin for this flip and this flip. This flip, we use a coin. This one, we use a random number generator.
Okay, I kind of understand.
That cleared it up? Yeah, it doesn't matter what you're using. This comes up 25%, or this comes up 50% of the time, this comes up 50% of the time, so this comes up 25% of the time. Right? Is it right? Okay. She's confirmed. All right. So, another intuition check. See if we can get you again. I flip a coin 5 times. Which of these are more likely outcomes? I just get heads every time, or that I get a heads and a tails and a heads and a heads and a tails? Which one's more likely? The bottom one is way more likely.
No, well, the way you worded it, you're like a heads, then a tails, then a
Yeah.
tails. So you're.
I'm intentionally trying to get them to give me the wrong answer. The answer is they're the same. This outcome has the same probability as this outcome.
You are
Flipping a
cheating
heads and a
us.
tails and a heads then a heads then a tails is just as likely as flipping a heads then a heads then a heads then a heads then a heads.
Okay.
Why?
There's a 50% chance of flipping a heads. there's a 25% chance of flipping a tails after flipping a heads.
Why?
What are all the possible outcomes once we've gone up to 2 flips? H, 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 T, T, H, T, T. Those are all equally likely, right? So far getting this and getting this are the exact same.
Yeah.
Now, when we make the 3rd flip, though, that's where all the difference comes from, right?
Sure.
Sure. No, it doesn't change anything.
Okay.
Right? Now if we expand this out, you're going to make me write 8 rows. So let me repeat. H, H, T, T, H. If we're flipping twice. And T, T. Now if we're flipping 3 times, all our possible outcomes are heads, 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 tails, 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 tails. Here's all our possible outcomes. And they're all equally likely. They're each 1/8 likely, right? And this is just as likely as this, 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 is just as likely as this. Right? Are you skeptical?
I'm just genuinely confused.
Do you understand what I mean when I write 3 H's like this? I mean, you flip the heads,
Yeah.
then you flip the heads, then you flip the heads. That happens 1/8 of the time. 1/8 of the time this happens. 1/8 of the time this happens, etc. Does that make sense? No? Yes? Is there any reason that this should be more likely than this?
No. No. But then it doesn't make sense with the 2 things. Oh wait, yes it does. But some of them are the same.
Same likely? They're all the same likely. I don't know what you mean by the same.
Okay, no.
Good? Okay. So now that we've done that, let's actually go back to the example. So what could our sample space be here for tossing a coin 5 times? How might we do our S?
It's not.
So it's gonna be like
It'd be
How many possible outcomes are there here? When I flip a coin 5 times, how many possible outcomes are there?
2 to the power of 5.
2 to the 5, which is 32.
Yeah.
Right. So you're counting something binary 5 times. So whatever it should be, we should alternate between binary things 5 times. So something like heads, 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 heads might be something in there. And then we might have a heads, 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 tails. And then we might have a heads, 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 tails, heads, etc. All the way until we get to tails, 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 tails. Right? Sample space could look something like that. Or that could be our set of outcomes. This is the set of all possible outcomes of flipping a coin 5 times. And we can make our probability function just 1 over 32, right? 1 over the size of S, if it's a fair coin. So, well, to be very explicit, our sample space, remember, is always the ordered pair SP, where S is this and P is this. Make sense? Anything weird? Okay, let's do one more, coming back to just a very concrete example that has nothing to do with the real world. So we're going to create a sample space where S is 1, 2, 3, 4, and we have P as a function from S to R by P of 1 is 0.1, P of 2 is 0.4, P of 3 is 0.1, P of 4 is 0, P of 5 is 0.2, P of 6 is 0.2. Completely random sample space. What does this go to? Who knows? Doesn't matter. The point is this a sample space?
Yeah.
No.
What's wrong with it?
it doesn't add up to 1.
Yeah. And why do you have P5 and P6 and 5 and 6 aren't in S?
That is a good question. Because I made a mistake. 5, 6. Good catch. Should have done that intentionally.
Okay, now it's a sample space.
Now is it a sample space?
Mhm.
Do numbers add up to 1? Are there any negative numbers? Alright, so yeah, we're good. And just want to make sure you guys are comfortable with this sum notation. So I want to make sure you understand, what do we mean when we write just this? The sum of all our probability functions for every little s in big S. Big S is the numbers 1, 2, 3, 4, 5, 6, so we're saying plug in 1 to this, plus what you get when you plug in 2, plus what you get when you plug in 3, plus what you get when you plug in 4, going all the way through the set S. So this is shorthand for this sum right here. Make sense?
Mhm.
Okay. So there you go. It's a sample space. And that's it. That's all we have for sample spaces. Any questions? All right. We can stop the recording, but give you guys another problem.